Welcome to the next lecture in the course Transport Processes in Biological Systems, Transport Phenomena in Biological Systems. I am going to use these terms interchangeably, so please don't get confused. Transport processes, transport phenomena, they are used in the same sense in this course. In the previous lecture, we saw some basic aspects of the course. Then we looked at, towards the end of the lecture, the conserved quantities. That is, we said that we know some physical quantities are conserved in a process. The left hand side equals the right hand side is something that conservation principle gives to us, which is a very big thing for analysis. The conserved physical quantities could be mass, momentum, energy, charge, and so on and so forth. There are other quantities, other physical quantities that are conserved, but we are going to look at these four in this course. That is good for biological systems, or good enough for biological systems analysis at this stage. Whenever it is necessary, we could look at the other aspects also. Just to give you an example, the most other disciplines of engineering, for example, chemical, metallurgical, mechanical, let us say aerospace, and so on and so forth, civil, they typically look at momentum conservation, mass conservation, energy conservation predominantly. Charge conservation predominantly the electrical engineers look at, the biological engineers, the other engineers don't look at them. Whereas for biological engineering, to manipulate biological systems, we need to look at all these four conserved quantities. We said we would look at the fluxes of these conserved quantities. That would be our major focus in this course. And we also defined the flux of a quantity, flux of mass, for example, mass flux equals mass per unit time that moves from one place to another per unit area in the direction, if the mass movement is in this direction, in the direction that is perpendicular to the direction of transfer. It could be momentum flux, it could be energy flux, it could be charge flux. Charge flux is the amount of charge transferred per unit time across a unit area or per unit area in the direction perpendicular to the direction of transfer. This is where we finished up the last time. Let us move further. Mass, it's so important, mass conservation is so important. Let us look at the conservation aspects alone first, for mass alone, because it happens to be such an important principle, and then look at the flux aspects of mass. Okay. We will just do this for mass, we will not do this for momentum, energy and charge. For the mass, because it is so useful, we will look at mass conservation alone first. We all know that mass can neither be created nor destroyed. Okay. This we have known for a very long time. That is what we mean by saying that mass is conserved. There are a couple of riders though. This assumes that we are not dealing with nuclear reactions. Why? Because in nuclear reactions, mass to energy conversion is possible. In fact, that is the essence of getting nuclear energy. Mass gets converted to energy. And it is assumed that we are not traveling at speeds close to that of light. Why? Because we know that when speeds reach light speeds, there is mass dilation, and such situations are not considered in this case. Okay. Apart from these two aspects, the rest, which is applicable a lot of times, okay, a lot of times of interest to us, in those times the mass conservation is definitely valid. So, what we are going to do is first review some applications of the mass conservation principles, and we will also extend it. You could have, or you would have done some of this in the material and energy balances course that you, or a material and energy balances course that you would have taken earlier in the curriculum. That is fine. So, if you have already done that, you could look at this as some sort of a review. But this is so important that I thought we should take a look at it in some sort of a review mode at least, so that we are sure that we are at the same base level. Okay. That is the reason why I am doing this. If you are very comfortable with this part of the lecture, that does not matter. It will probably give you a different view of looking at mass conservation. Maybe you did not look at it in totality and so on and so forth. So, even if you have done a course in material and energy balances, this could turn out to be useful. Just look for the viewpoint. For the others, just start picking up the principle. Okay. Before we even get into this mass conservation, let us spend a little bit of time on what is called the rate concept. Okay. This might seem trivial to some of you, but it is not. The misunderstanding of this aspect, or the not appreciating the fact that this is so central to any engineering analysis, leads to a lot of confusion even much after graduation. You would have graduated with a degree, even done a higher degree, a PhD and so on and so forth. But somehow people have not internalized this, and that leads to a lot of confusion when people get into analysis. Okay, and therefore, let us spend a little bit of time right here, right in the beginning, to understand the importance of looking at rates of various different things in an engineering context. Okay. To do this, let me take the case of a typical odd scenario. This is especially in Chennai. Many summers there is water shortage. Okay. The water supply reduces. The planning, of course, still needs to be much better, and so on and so forth. Some years it is not so bad. Some years it is really bad. When the water supply gets bad, people use tankers, or the government provides water to various localities in tankers. Tankers are these lorries with cylindrical containers that have a capacity to carry water. These container lorries go to the water filling stations where water is filled, water supply is there somehow, water is filled, and then they go and distribute the water to various localities. Okay. For a certain payment, of course. You will have to pay for this in certain situations. In some cases, it is supplied free of cost depending on the situation. So, let us say that we are looking at that situation here. So, this you could see is some representation of the container that contains water, and this is a part of the lorry on which the container rests, and this is the water stream that is flowing to fill this container. Okay, this is the situation that we have in our hand. Let us say that we are filling a water tank, and the volume of this container or the tank is 12,000 liters. Okay, why did I choose this 12,000? Because the smaller tankers in Chennai are 8,000 liters, the large tankers are 16,000 liters. So, I chosen an average value of 12,000 liters. Okay. When the tank is full, what do you think is the mass of water in the tank? Can you work it out? Might be a good gelling of your brain to work things out. Let me give you probably a couple of minutes. Why don't you work this out? What is the mass of water in the tank? And we know that the volume of water in the tank when it is full is 12,000 liters. Go ahead, please. Give you some time. How would you go about that? What we need is mass. Okay. What we know is volume, right? And what we also know, we are all engineers, we know from school that the density of water is 1 gram per centimeter cubed, and if you convert that, that goes to 1000 kilograms per meter cubed. That is the density of water. Okay. And what is the definition of density? Density is mass per unit volume, or mass by volume equals density. Mass by volume equals density. We know the density, we know the volume, we need mass, right? So, mass is nothing but density times volume. Density is 1000 kilogram per meter cubed, and volume is 12,000 liters. 1000 liters is 1 meter cubed, and therefore 12,000 liters is 12 meter cubed, and therefore the mass here, mass of water in this tank when it is full is 12,000 kgs. Okay. If you got it, it's fine. Otherwise, pause the video here, take some time out, work this out completely. Nothing but from the definition of density, mass per unit volume. Mass by volume equals density. We know volume, we know density, therefore we need to multiply density and volume to get mass, and that's what we did. There was some unit conversion here because the values were given in different unit systems. That's it. That's what we did. Go ahead, do this, feel comfortable with this, pause the video till you feel comfortable, and then start up the video. Okay. I'm going to continue. I'm assuming that you're going to pause it till you feel comfortable. My interest is this: how long would it take to fill the tank? And that I'm going to call as time t. How long would it take to fill the tank? This is a very typical engineering question. You have a tanker going and filling water, it is going into a filling station. How long should the tanker be there? It's a very practical question to ask in terms of design. Suppose somebody is designing the distribution of water system, this is an important data to have. How long does it take to fill the tank? Right? It's a very engineering input to have. How would you go about doing it? Think about it. Pause the video here. Think about it. Hopefully you had some ideas. You would have realized that you need to have an idea of the rate at which the water is being filled to figure out the time of filling. Okay. Hopefully you got there. If the rate is 10 kilogram per second, it would take 1200 seconds, or that's about 20 minutes. That is 20 minutes. If the input rate is 20 kilogram per second, the time it takes is 600 seconds or 10 minutes. If the input rate is 50 kilogram per second of water, the time that it takes for filling is 240 seconds or 4 minutes. Okay. In other words, if we know the rate of input, water input, then the time is nothing but mass per rate, because rate is nothing but mass per time, right? We need the time, therefore that is mass per rate, as simple as that. So once we know the rate, okay, give importance to this or focus on this, the input rate, then we can find out the time. And it so happens in these situations, the rate is typically about 20 kilogram per second, because it typically takes about 10 minutes to fill the tanker. If it is smaller than that, it takes too long to fill a tanker, that's not very practical. If it needs to be larger than that, then the pumping power needs to be that much higher. You need to have much more expensive pumps, higher capacity, and therefore more expensive pumps, and so on and so forth. May not be really helpful in the overall economic analysis. And that way, this becomes a very crucial information to have. Let's get back to our discussion. Suppose there is a hole in the tanker which oozes water at the rate of 5 kilogram per second. How long would it take to fill the tank? Can you work this out? Pause the video here. Let me read it out again, or you could read it out as many times as you want to understand completely. I'll read it out once. Suppose there is a hole in the tanker which oozes water at the rate of 5 kilogram per second. How long would it take to fill the tank? Can you work this out? Pause the video, work this out please. Typically about 5 minutes. Hope that you are able to work this out. I would go about it like this. The net rate, net is what? There is a rate at which water is being filled, there is a rate at which water is oozing out, right? Therefore, the net rate of water being filled is the input rate of water minus the output rate of water. The input rate of water is 20, the output rate of water is 5. 20 minus 5 is the net rate at which water is being filled, so 15 kilogram per second. Once we have this, once we are focused on the rate, we have this number, and then it becomes very simple that the time is nothing but mass per rate, 12,000 kilogram per second by 15 kilogram per second, 12,000 kilogram by 15 kilogram per second, that is 800 seconds or 13.3 minutes. If you had not focused on the rate concept, it's a rather confusing situation to be in. You would have probably experienced that this much is coming in, this much is going out, how do I go about doing this? It's a standard confusion. Whereas the minute you focus on rates, once you focus on the rate, it's a very simple, straightforward calculation. Okay. That is the need to look at the rate concept. Let me give you one more example just to drive home the point a little better. Now, suppose that in addition to the leak, there is some mechanism inside the tank itself that is generating water. Okay. This is fiction, therefore, we will say some reaction generates water inside, and the rate at which it generates water inside is 1 kilogram per second, and some other reaction in which water is used up inside the tank at 0.25 kilogram per second, all of which are happening simultaneously. There is input rate filling in, there is oozing out, and then there is generation of water, and then there is consumption of water, everything happening inside that tank, okay, happening simultaneously inside the tank. Inside that simultaneous thing is the killer. How long would it take to fill the tank? Okay, pause the video here, go forward and work it out. I hope you worked it out by looking at rates. Again, if you focus on the net rate, the net rate is rate at which it comes in, rate at which it goes out, rate at which it getting consumed by a reaction, rate at which something is being added, the water is being added by another reaction. Okay. So, there are two things that are adding, there are two things that are subtracting. So, input and generation are adding, output and consumption are subtracting. Input rate is 20 kilogram per second, output rate is 5 kilogram per second, generation rate is 1 kilogram per second, consumption rate is 0.25 kilogram per second. So, the algebraic sum 20 minus 5 plus 1 minus 0.25 is 15.75 kilogram per second. So, this is the rate at which the water is getting accumulated inside the tank, and that is the rate of change of water mass with time in the tank, which we can call as a system. System is something that we focus our attention on, as you would already know. Therefore, the time that it would take to fill under these conditions is mass divided by the net rate, 12,000 kgs divided by 15.75, that is 761.9 seconds or 12.7 minutes. So, the moment you focus on the rate, it becomes a simple calculation. Okay. That is the reason for us to focus on rates. Okay. If you recall, when you were in high school, the focus would have predominantly been on mass, amount, volume, and so on and so forth. The moment you came into engineering, people started talking about rates, right? You wouldn't have probably given too much attention, but you need to realize that there is a big need to talk in terms of rates. Okay? Once you start talking in terms of rates, everything engineering related becomes very simple. Anything dynamic related, for that matter, a dynamic system, cell is a dynamic system, anything that is dynamic in nature, anything that changes with time, once you bring in rates, it becomes very simple to look at it, or you need to start looking at things only in terms of rates. So, rate is a fundamental in terms of usefulness, that is what I mean, parameter. You need to start thinking in terms of rates rather than amounts. By amounts, I mean mass or volume, as you did in school. That is the main point, that is the important aspect that I am trying to drive home here. Okay. What we will do is, we will take a break here. We have been at it for some time now. If it is too long, again it becomes a little tiring. So, let us take a break here and continue in the next lecture. See you.